Chapter 5, Chemistry of Transitions Elements. So first, what is transitions elements? So it's a D block element that forms one or more stable ions with incomplete D orbitals. Okay, so first of all, you need to know they are using D orbitals. For example, you can see here 3D1, 3D2, 3D3. So they are using D orbitals. And their D orbitals must have incomplete D orbitals. That means must have electrons, cannot be empty, cannot be full. So cannot be empty and cannot be full. That is meant by incomplete. So not empty and not full. So that is incomplete D orbitals. So for example, over here, you can see scandium. Scandium can form stable ions with oxidation state positive 3. And in that situation, you have to remove away 3 electrons here. 3 electrons here. So first you remove from 4s2, then you remove from 3d1. So at the end, scandium 3 plus is having AR, the electronic configurations of argon, and it does not fulfill the condition here where they want incomplete d orbitals. This one is empty d orbitals, and because of that, is not scandium is not a transition element. Okay? Because when they form a stable ion of scandium 3 plus, it has empty d orbitals. So if we look at titanium, the atom has 3d2 and 4s2. So of course, you should be able to imagine if they form titanium positive 4, titanium 4 plus, the oxidation state is positive 4. So it loses 4 electrons. In that case, it is empty d orbital. But the thing is, it can also form a stable ion of positive 3. So if they form positive 3, it means you are going to remove 3 electrons from here. So 2 from the 4s2 and 1 from the 3d2. So end up with titanium is having argon followed by 3d1. So this is the incomplete d orbitals. We have 1 electron there. So titanium is the first transition element. Scandium is not. Scandium, you can call it D block elements because they are using D orbital, but you cannot call it transition element. It is D block, but it's not transition. Vanadium. So vanadium, they can form quite many types of stable ions, positive 2, positive 3, positive 4, and positive 5. So it is transition element. Chromium also. Okay, and then and so on. Okay, so let's see anything special here. You can see here we have 3D1, 3D2, 3D3. This one is a bit special. If we follow the trend, it's supposed to be 3D4. It's supposed to be 3D4, 3D4 and 4s2. Supposed to be this 3D4 and 4s2. So the thing is, if there are lack of 1 electron to be half filled, so the electrons from 4s2 can move to 3d4 to make it to half filled 3d5, and this one become 4s1. So this is more stable. more stable. So that's why we have this special situation that don't follow the trend to be 3d4 and 4s2, but one electron moves to 3d4 to make it to half filled, which is more stable. You can see here, chromium and copper have anomalous configuration. That means they have special configuration. So chromium, which is supposed to have 3d4, then what happened is the 4s electrons demoted to the 3d4 to make the 3d shell having a half-filled 3d shell. So that the reason that they do so is to be more stable. And now let's move on to the next one. Manganese 3d5 4s2. So the trend continue actually, so only chromium is a bit special. After that the trend continue, 3d5 4s2, 3d6 4s2, 3d7 4s2, 3d8 4s2, and this one, if we follow the trend, is supposed to be 3d9 4s2. So supposed to be 3d9 4s2. So what happened at the end is it is lack of one to be fully filled, and because of that, the electron from the 4s orbital can transfer here to make it fully filled, and that is more stable. 3d10 4s1 at the end. Okay, more stable. So again, the reason that they do so is to be more stable. So that's why you see here, copper, 4s electron demoted. That means they shift to 3d9 to make it to 3d10. So to form the 3d10, which is fully filled, this is typo error, fully filled 3d shell. Okay, so we move on to this one. Zinc, 3d10 4s2. And zinc, if they change to zinc 2 plus, right? Zinc 2 plus, so it becomes argon and 3d10. So at the end, zinc does not fulfill incomplete d orbitals. So which means zinc is not a transition element. It is fully filled. It is full. So it cannot be full. It must be incomplete. So for zinc, it cannot be transition element. You can say it is D block, but it is not transition element. So from here, from this table, we have to say that there are two members which are D block, but they are not transitions element. Okay, so now let's move on. They mentioned what I said just now. They said scandium and zinc are not transitions metals because scandium 3 plus has no electrons in the d orbitals. No electron. So as you can see, after argon, nothing already. So this is empty. It is not transition metal because scandium 3 plus has empty d orbitals. Zinc 2 plus is not transition element because it contains full or fully filled d orbitals. Chromium and copper, this one we have discussed through, so I skip this. So like what I said, they have special electronic configuration because they want to create a more stable configuration. Now these are the extra notes they mentioned here. They said when electrons added, fill 4s before 3d. So 4s come first. Why 4s come first? Because 4s has a lower energy level. When it is empty, 4s has lower energy level compared to 3d. Okay, so that's why 4s is filled up first. Now next point, when electrons remove from 4s before 3d. So how come now it is 4s again? So we have to take it in this way. When electrons are filled up in 4s orbital, then 4s orbital has higher energy level. So the idea is, when you remove electrons, we remove from the orbitals with higher energy level. Okay, so that's why 4s first, because 4s has higher energy level after you fill up with electrons. Okay, so I put it here. Before electrons are filled, 4s has lower energy level. This one, after electrons are filled, 4s has higher energy level. So that is the reason. Okay, so we just move on. 5.2. 5.2 D orbitals. Okay, so you know transitions elements, D orbitals are involved, as you can see there. And we have to know there are 5 orbitals over there. So D orbitals consists of 5 orbitals. Okay, just a quick revision. So you know, 3, normally we write like this, or we draw it in this way. 3D, right, is 5 boxes in this way. And then 4s is 1 box, 1 orbital. So 3D has 5 orbitals. Okay, now let us look at the shape of the orbitals. So the first one, we have dxy. Dxy, right, we take it in this way. The orbital is the dumbbell shaped, and it lies in between of the x-axis and the y-axis. So as you can see here, the black one, or the gray color one, this is in between of the x-axis and the y-axis. And the other orbitals is the white color dumbbell. So again, this is in between of the x-axis and the y-axis. So that is dxy, which have orbitals in between the 2 axes mentioned here. So the next one, dxz. So the first orbital, the gray color orbital, is between of the x and z axis. And then the second orbital, the white color orbital, is again in between of the x and the z axis. Okay, dyz, same idea. It is between of y and z axis, and the other one is also in between of y and z axis. Okay, so these 3 are normally known as one group. Okay, the first type lah. Okay, I call it first type. The first type of d orbitals, where the orbitals is staying in between of 2 axes. In between, this is the first type. And the second types of d orbitals is the one with power 2. So we have dx squared minus y squared. You can see power 2 there. So for this kind of d orbitals, you will see the orbital is on the axis. Just now, this is between the axis. This is on the axis. So if you have x squared minus y squared, that means one orbital is on the x-axis, another orbital is on the y-axis. Okay, so after that, dz squared is where the orbitals on the z-axis. So these 2, I call it type 2. So this one I call it type 1. So there are 3 of these where I call it type 1, and then there are 2 of these where I call it type 2. Okay, so the 5 orbitals here, 3 are between axes, and 2 are where the orbitals stay on the axis. Now, let's see the point here. dxy, dxz, and dyz have d orbitals in between axes. Huh? And dx square minus y square and dz square have orbital along axis. So I already explained. And why dz square looks different format from this? So that I try to explain. dz square is formed by the merging of dx square minus z square and dy square minus z square. It is this and this that merge. Of course, you should be able to predict x square minus z square means the orbital on the x-axis and the orbital on the z-axis. This is orbital on the y-axis, orbital on the z-axis. These two merge, and at the end, it becomes on the z-axis only. Okay, how they merge? No need to care lah. Okay, so we just take it only. Now let's move on. 5.3. So 5.3 is where we learn the physical properties of transition element. So you can see here, transition metals have partially filled d orbitals. So because of partially filled d orbitals, some properties come out from these situations. Okay, so let's see here first on the left. Nuclear attraction shielded by 3D electrons. Okay, so that means the 3D electron is like blocking. It's like blocking. It's like blocking the nuclear attractions of the nucleus. Okay, so it's like blocking. That is shielded. Okay, shielded, blocking. And we look at the consequence because of the shielding of the 3D electrons. So that's it. Changes in atomic and ionic radii small across period. This is the consequence of the shielding. You know the nuclear attraction, right? Imagine that when you go along the D blocks, there are more and more protons. So more and more protons by right. The protons supposed to attract the electrons and make the D block elements to be smaller and smaller. By right, it's supposed to be like that one. More and more proton, greater and greater nuclear attraction. It's supposed to make the atom smaller and smaller, but at the end, it is about the same size. About the same size. So over here, the explanation is because the nuclear attraction is blocked by the 3D electrons. Okay, so they want to attract the 4s electron, cannot. It's blocked by the 3D electrons. So because of that, their size is more or less the same. So the nucleus or the protons can't attract well because of the 3D electrons. So same size or more or less the same size, and after that, it end up with a properties here in blue color. Small increase in first ionization energy across transition elements period. So because of the shielding, right, their first ionization energy is more or less the same. More or less the same. So that means imagine all these have more or less the same first ionization energy. So why? Because they have the same size, and the protons which supposed to attract stronger and stronger cannot do so because of the shielding effect. Okay, so that's why the ionization energy is more or less the same. Now, next one, small energy difference between 4s and 3d. Small energy difference. So this one we should know long time ago, where 3d orbitals, 4s orbitals, their energy level are very close to each other. very close to each other. So at the same time, remember that before electrons are filled, 4s is a little bit lower than 3d. After you fill up with electron, 4s is a little bit higher than 3d. So this is something that you need to know, but their difference is very small. So since the difference is very small, it ends up with a properties here. Successful IE, successful ionization energy, closer together, hence variable oxidation states. So what is variable oxidation state is something like this, Vanadium can form +2, +3, +4, +5. That is variable oxidation state. And why they can do so? Because, for example, vanadium, you want it to remove 2 electrons, it's kind of easy. Remove from 4s2. And if you want it to remove electron from 3d3, it's kind of easy also, because the energy level between this and this are just more or less the same. So removing 2 electrons is more or less as easy as removing 3 electrons. Okay, so, or removing 4 electrons. So, because of that, the successful ionization energy are closer together. They don't increase too much. Okay? They don't increase too much. So, and because of that, they can form all kind of oxidation state. Okay, so it's because of the small difference in energy level. So next one, greater number of delocalized electrons. So because of small energy difference, right? So like what I said, removing 2 electron or removing 3 electron or 4 electron or 5 electron doesn't involve a big amount of a big increase of energy, and because of that, they can form ions of different oxidation states, and at the meantime, they can have delocalized electrons to be donated. You can donate 2 electrons, you can donate 3 electrons, you can donate 4 electrons or 5 electrons, to form the delocalized electrons. Okay, so because of that, the electrical conductivity is better compared to calcium. Why calcium? Calcium can donate 2 electrons only. 2 electrons only, so it's fixed. 1 atoms of calcium donate 2 electrons to form the delocalized electrons. But as you can see, vanadium can donate up to 5, so greater number of delocalized electron and hence greater electrical conductivity. And delocalized electrons also affect the metallic bonds. So if they can donate greater number of delocalized electrons, then it forms a stronger metallic bonds. So with a stronger magnetic bond, then the melting point is higher. It's higher compared to group 2. Group 2, calcium. Calcium. So why calcium? Just for your information, calcium is just 1 position before scandium. If you look at periodic table, you will know 1 position before scandium. Okay, so it's just neighbor to all this. Calcium is a neighbor to all this. So use calcium as comparison is because of that. They are at the same period after all. Now, stronger metallic bond make the lattice more closely packed together. So they have stronger metallic bond, then they are closer together because the metallic bond works here, attract and make them closer together. The lattice is closer. Okay, and because of that, they have smaller atomic radius compared to calcium. So because of stronger metallic bond. Okay, so now when we look at this, smaller volume and higher atomic mass. This one is related to this. They are closely packed now. And because they are closely packed, then their volume is smaller and their mass is higher because of closely packed. And because of that, they have higher density than calcium. So this is like heavy metal, heavy metals. Huh? So they are heavy, or in other words, they are higher in density. Okay, so altogether, how many physical properties? You just look at the blue color one. So 1, 2, 3, 4, 5, 6. 6 physical properties over here.